In the previous lecture, I mentioned a simple criterion how to decide whether a number is divisible by 3. I mean, if I want to decide whether 1, 2, 3, 5, 7, 9 is divisible by 3, what I do is just take this number, compute the sum of digits. I see that it is divisible by 3. So here 3, 3, 12, 9. So the sum is divisible by 3, and then I know that this number is divisible by 3. Same criterion works with division by 9. The number is divisible by 9, you can only the sum of digits is divisible by 9. There is a criterion with 11. It is about taking alternating sum of digits. With 11 it works like this: 1 minus 2 plus 3 minus 5 plus 7 minus 9. If such a sum is divisible by 11, then the number is divisible by 11. And the question was, well, what about 17? How can I decide whether a huge number is divisible by 17 if I just look at this number? So let me try to answer this question. I mean, it is simple and it is actually on the topic that we are covering. So let me call it kind of divisibility criteria. Well, one criterion. If you have a number like this, a not a 1, a n, let me put kind of bar over it to indicate that it's not a product of these things, it is actually a number whose digits are a not, a 1, a n. So a number written in base 10 with digits a not, a n. So the claim is as follows. This thing, this number has the same remainder modulo 3 as the number with digits. In fact, not only modulo 3, even modulo 9, even stronger. Another thing, if you want to compute its remainder modulo 11, it is an minus an minus 1 plus an minus 2 minus and so on plus minus 1 to the power 0, so n a naught modulo 11. So it gives you a kind of criterion when is a number divisible by 11. Exactly when this alternating sum of its digits is divisible by 11. Very simple test. And the question is there such a test for 17? Well, the answer is yes, there is such a test. It's not that memorable, maybe, but still useful. Let me not explain what the test is. You'll just invent. It's really simple. So let me prove it. For both parts, basically. What happens here, this number, a not, a 1, a n, I can write it in the following way. It is the last digit plus 10 times plus that one digit plus and so on plus 10 to the power n times the very first one. I mean, it's just another way to write the same number. What is 15 is 10 plus 5. What is 37 is 7 plus 10 times 3. So the same thing here. What is a number written in this way? It is the last digit plus 10 times last one digit plus 100 times the next digit, and so on. And now it's obvious that 10 to the power n is congruent to 1 modulo 9. So the first criterion follows. 10 to the power n is congruent to minus 1 to the power n modulo 11. Second criterion follows. So this number, modulo 11, is the same as an minus 1 plus the next one minus the next one, and so on. What about 17? Well, kind of more complicated, but not much more complicated. So criterion for 17. No, let me do it for 7 first. For 7 is simpler. Well, what do we have to do? We have to take 10 and raise it to different powers modulo 7. So 10 to the power 0 is 1, 10 is to the power 1 is 3, 10 squared is 3 squared, which is 2. 10 cubed is 2 times 10 is 20, so 20 is minus 1. Modulo 7, so everything here is modulo 7. Next one is going to be minus 1 times 10, so it's minus 10, which is minus 3. Modulo 7. Well, am I going to repeat myself at some point?
You can make that time and read it.
Yes, of course. And even better, I know that 10 to the power 6 will be equal to 1. So I'm going to come back to 1 after 6 steps, at most 6 steps, because of Fermat's little theory, once again. So 10 to the power 5 is negative 2, modulo 7. And then it starts repeating. 10 to the power 6 is 1, modulo 7. And then, once again, 1. I keep multiplying by 10. And then, like this. So what is the criterion for divisibility by 7? Well, this number is congruent to the following thing. It's A0 plus 3 times A1 plus 2 times A2 minus A3 minus 3 A4 minus 2 A5 plus A6 plus 3 A7 plus 2 A8 minus plus, and so on and so on and so on. Yes.
Isn't A and zeros of units, is it?
Yes, you're right. This was later to correct this. I guess there's the number in here. We'll see there. So that's the zeros. Oh, the last digit, you want the last digit, and so next. So here you have a way to compute what is the remainder of the complicated number modulo 7, or to test whether a number is divisible by 7. Compute the sum of digits with these coefficients, kind of linear combination of digits with these simple coefficients. You just have to remember the sequence. 1, 3, 2, minus 1, minus 3, minus 2. 1, 3, 2, minus 1, minus 3, minus 2. Okay, so here you have to remember a sequence of coefficients of length kind of 6. What is going to happen with 17? Now you can answer. 16, yes. So Fermat's little theorem tells me that in the worst case scenario, I mean, I'm not sure, maybe the sequence actually will repeat itself after less than 17 steps, less than 16 steps. It could happen. But even in the worst case scenario, there will be some sequence here of length at most 16, which will be repeating itself. 10 to larger and larger powers will be just the numbers in this sequence. So now it's up to you to actually compute it, remember it, and if you're actually using, well, if you're actually dividing by 17 very often, well, maybe you should remember it. I don't, so I have no idea. Okay, maybe any other questions? So now let's go back to the question of raising it to some fractional number, which means extracting the root. Going back, well, so once again, our problem. Computing e to the power 1 over k modulo m. So more precisely, oh, that's kind of shorthand for what the problem is. The actual problem is solving the equation x to the power k is congruent to e modulo m for x. Something like this. Let me just say that it's an example. So let's do the fifth congruent to 2 modulo 37. So we want to find some remainder, some residue such that this number raised to the power of 5 will be congruent to 2 modulo 37. So maybe any suggestions?
You know how to consider power,
Okay.
and root is just the inverse.
Okay, it's kind of numerous operation, but how to reverse the complicated computation. I mean, we call how we actually compute the powers. We either multiply the number by itself enough times. How do we compute? How do we multiply a number by itself 1 of these times? No problems.
How can we compute the power of 2 to the power of 5?
2 to the power of 5.
And then using 1 to the power. Or we can find use the Fermat's Euler theorem.
Okay.
Find the order 537.
Okay, so let's see what Fermat's little theorem tells you. So first of all, well, before I go to the kind of shorter way, let me give you an obvious answer which should have come to your mind. Just take all the possible x's from 0 to 36, raise each one of them to the power 5, and compare with 2. That's kind of the most naive algorithm, and well, it kind of works. I mean, it takes long. If this 37 is replaced by a number with 100 digits, well, you won't be able to finish this way. But still, it is an algorithm that kind of works. Works slowly, but it works. The better one is, yes, indeed, it is about using Fermat's-Little theorem, or Euler's theorem. In this case, 37 is a prime number, hopefully. Yes, looks like a prime number. So it's not divisible by 2, it's not divisible by 3, it's not divisible by 5, it's not divisible by 7, and that's enough. If it has a factor which is greater than 7, then 37 divided by this factor will be smaller than 7. So you already checked the number. This number is prime. So within Fermat's-Little theorem, any number raised to the power 36 is congruent to 1 modulo 37 will give a is not divisible by 37. Well, let's see this code. Let me say a little bit more. If I take any number and raise it to the power 36 times any k, any multiple of 36, still I get 1 to the power k, which is still 1. So raising a number to any multiple of 36 will gives just 1. So if we use it to rewrite this equation in a slightly different way. So x to the power 5 is congruent to 2 modulo 37. Well, it implies that x to the power 5 plus any multiple of 36 is congruent to 2.
You can write a 36k as 1 plus 36, 1 plus 5 and times b, times another b, right?
Okay, so you're right. I can compute x by doing the following trick. I can take x and write it as just x plus to the power 1 plus any multiple of 36. That's simple. Now, if 1 plus 36k is equal to some multiple of 5, which, well, we can assume. We know how to solve such equations. This is a linear equation about k and about n. So in general, we can solve such equations. If this number is a multiple of 5, I will be able to rewrite this in the following way. X to the power 5n. Or I can rewrite it in the way x to the power 5 to the power n. But then x to the power 5 is already known. It is just 2. So it is congruent to 2 to the power n modulo 37. So if you want if you know this, what is x to the power 5, and you want to know what is x, well, x itself is not convenient enough, well, you just can't use directly this information. But by Fermat's theorem, you can rewrite x in a more convenient way. You can rewrite it as x to the power 1 plus any multiple of 36. If you can manage to make this exponent nice enough, basically just divisible by 5, then you already know what is x to the power 5. Well, you already know what is x to any multiple of 5. And this is enough. So let's actually do this in this example. So in this example, I want to actually solve this equation. 1 plus a multiple of 36 is a multiple of 5. How do we solve these equations? Well, we know how to do it. We just devoted the lecture to how to solve linear equations. So 1 plus 36k is 5m. We'll just rewrite this in the following way. It's 5m 36k is equal to 1. We know that this equation is solvable because the GCD of 5 and 36 is exactly 1. So we know that this is solvable equation. How to solve it? Well, Euclid's algorithm. Just take the thing and rewrite it as 5 times n minus, divide 36 by 5 with remainder. It is 7 and remainder 1. So I can rewrite it in this way. Now my equation is basically solved. I can take any k, I can take any number n minus 7k, and this will produce me, so the solution is k is 1 plus 5 times n minus 7k. I can take, let me do it properly, I'll introduce a new variable n prime, which is n minus 7k. And then this equation is basically just k is 1 plus 5 n prime. Given any number n prime, I can find